So far, we've discussed Coulomb's law and current. What we need to get into next is energy. Because if we remember, the conservation of energy is an extremely powerful concept that allows us to switch between potential and kinetic types of energy with a lot of ease. In the same way that we are able to easily switch between concepts in mechanics, we want to be able to do that in electrodynamics. However, that energy is going to look slightly differently in order to be useful. First, let's remember our law of universal gravitation, because it looks so much like Coulomb's law. Our law of universal gravitation, if we wanted to convert this into an energy formula, all we would need to do is remember that energy, in the form of work being put into a system, is found by force times distance. In order to make this work, all we need to do is multiply the whole thing by distance. So that times distance, this side times distance, that d is just going to cancel out that r squared. So we end up with gravitational potential energy, g there, is negative. Remember, negative because that was just the frame of reference that we used for this. Capital G m over r. Now, remember that the way we've defined energy in a mechanical sense, we're able to measure it using the joule, which we get from these two guys right here. So the joule is itself a derived measurement made up of different measurements. Let's look at what those are. A force, remember, was an acceleration times a mass, then distance is a distance. Mass is measured in kilograms, acceleration is measured in meters per second squared, and distance is measured in meters. So if I put all of these together, a joule is really made of a kilogram meter squared per second squared. And herein lies the problem. While right in this equation, the things driving this, the masses, are right here in energy, I don't see anywhere in this definition that I have a coulomb. There's no charge in this definition. So we need a new way to think about energy for electrodynamics that's going to include the charge, because that is all over. Everything in electrodynamics runs based on that charge. If I'm not accounting for the charge, it gives me an extra step to try and figure everything out and compute it along with the conservation of energy. So first, let's figure that out. If I want to move Coulomb's law into energy, well then I'm gonna do this over here. I'm going to multiply both sides by distance, just like I did over here, and that's going to give me force, electromechanical, times distance, electrodynamics, is equal to K Q1 Q2 over R. So it does the same thing. However, this still doesn't give me a charge on this side. That's what I need. I need a charge on both sides of this equation in order to move freely within electrodynamics. So the way I'm going to do that is I'm just going to take one of these charges, I'm going to divide both sides by it. So I'm going to use Q2, divide both sides by Q2. It really doesn't matter which one I use, because at the end of the day, it's just going to be, I can label any charge Q1 or Q2. It's arbitrary. But when I do this, what I end up with is force times distance divided by charge is equal to Coulomb's constant times charge divided by that same distance. Okay. Now this gives us a very effective way to move freely between energy and electrodynamic forces. Now remember, dividing by charge, that really reminds me over here of whenever we would convert from gravitational energy into something like kinetic energy. Remember, that was Ke equals 1/2 mv squared. We were always able to cancel out that mass. That mass canceled out there, and that made our calculations really convenient. The same thing is going to happen with this. Now, we need to define this concept because this isn't energy anymore. See that charge right there? This whole part, this is a joule. Right here, this is a joule. But this is not. So what unit am I going to have? Well, first, let's circle this. This is going to be a joule. This down here is going to be a coulomb. So I've got joules per coulomb. What do we call that? Well, that is actually a unit that we are all very familiar with. It's the volt, as in voltage, as in the stuff that we rate our outlets, our batteries in. All the things that we charge need to be at a certain voltage. This is a concept that we're actually very familiar with. So a joule per coulomb, energy per charge, is a volt. See, when we're working with electrodynamics, we need to keep that energy in terms of charge because everything's going to work according to charge. So it's like asking, well, I've got this giant buildup of charge. Well, how much energy do I have here? I've got energy between these two charges, but how much is it? Well, it's going to be completely dependent on the other charges that they can interact with. So our definition of voltage is going to be a joule per coulomb, and we have two equations to describe it. And specifically, our definition, in more wordy terms, is going to be electrical potential energy. So it has this nice fancy name. A volt, by the way, is a unit of measurement. It is the unit of measurement for voltage. So we've got voltage measured in volts, abbreviated as a capital V. As a variable in equations, you might see this as a capital V or a capital E. Either one is generally used and fairly indistinguishable. They are fairly indistinguishable. We end up having some problems with that. So it's very important to keep in mind what units you're trying to deal with here, because E is also used for energy. In more advanced classes, you'll see it used for an electric field. Which is very similar to the volt. V, that could refer to volume in other cases. So we want to be careful that we know which context we're working in when we use these variables in our equations. Fortunately for our purposes, that is almost always going to be extremely obvious. And by the time you get to more advanced cases where you would need to be able to keep that in mind, your skill will have grown for this to not really be that much of a problem. But just keep in mind that depending on where you look, you might see voltage represented by an E or a V. Alright, so now we've got definitions for Coulomb's law, current, and voltage. We're really starting to get a really well-rounded view of these electrodynamics. We've got one more concept that we need to look at, but before we do that, let's try and understand voltage as far as the dynamic part of electrodynamics goes. Because right now this is just an equation. It's not quite a concept. So to make it more of a concept, let's think of it this way. If I've just got a random charge, let's call it a negative charge with 10 coulombs of charge, just floating in space, what's the voltage going to be? The other way I want to say that is, what is the potential energy going to be? And this is really, just by bringing this into the conversation, it really helps us understand why we need that charge there. Because the answer is, if I'm 10 meters away, what's my potential energy? Well, I don't actually have any potential energy. Because remember, that potential energy is all going to be dependent on that force. Without a second charge, I don't have any force. So all of it is potential. It is electrical potential, but until there's another charge there, there's not going to be any energy, there's not going to be any force. So how can we figure things out? How can we represent the idea that there might be a charge there? That's where voltage comes into play. Voltage is going to say, well, if there was a charge there, our energy would be based on how much charge there is. So, how much voltage am I going to have here at this point? I can easily just throw that into this equation. That's going to be K Q over R, or 9E9 times 10 divided by 10, which these will cancel out, and I'll have 9E9 volts. Nice and simple. If I go 100 meters away, how's that going to change my voltage? Well, with 10 coulombs, I'm now going to have 9E9 times 10 coulombs divided by 100 meters. Well, that's going to drop that down to an 8. I'm going to have 9E8 volts at 100 meters. Now remember, that is voltage that is energy per charge. So if I go back here and go force times distance over charge, and I put another charge out here, and I say I'm going to put a positive charge of, let's say, 5 coulombs. Well, I've got 9e to the 8 volts right here from this charge. Now I can actually do some calculations. So my voltage is equal to 9e8 volts. My distance, that's still going to be 100 meters. And my charge is going to be that 5 coulombs. So we can kind of flip-flop back and forth which charge we're using, but we need to keep in mind the context that we're working with here. This is my originating point, so I'm going to use this equation. This guy is my additional charge that I'm going to try and figure out the force for, so I'm going to use this equation. I could flip these back and forth, and I could say I want to know the voltage due to this 5 coulomb charge over here, but it really makes no difference. I'm going to end up with very similar numbers. So, right here, this is going to be voltage is equal to force times distance divided by charge. Let's rearrange to solve for force. So let's just make some space here. So voltage, so V times charge over distance will give me my force. Okay, so my voltage is 9E8 times 5 coulomb charge divided by 100 meters. Now remember that 5 coulombs and 10 coulombs are massive charges, and 100 meters really isn't that far, so this force is going to be astronomical. Let's go ahead and calculate it. We get a force of 45E6 newtons. All right. So the reason we have voltage is so that when we think of these charges, we have two options. One, a very convenient way to figure out how a charge placed in a spot is going to react to the other charges around it, and so that if we don't have a charge in that spot, we can still measure some amount of potential just so that we can get things prepared, so that we can have some idea of what's going to happen.